morning. This is topic 7.1, Introduction to Equilibrium. So the main objective today is to be able to explain the relationship between the occurrence of a reversible chemical or physical process and the establishment of equilibrium to experimental observations. So with this particular unit, it's all about equilibrium. So just so you know, this is 14 topics in this particular unit, so be mindful of that. All right, so many chemical reactions, they go, like when you think of chemical reaction, you should go from reactants to products, boom, boom, that's it. So the thing is though, is that they actually can be considered reversible, meaning they go back and forth between the products and reactants, and they use a double arrow to signify that. Shown right here. So in this reaction right here, you have water that is becoming a gas. So it's evaporating, but then also condensing in the same bottle. So that's why you have a reversible reaction. So you can think about that when you see a bottle with condensation on the top. That means it's going from gas to liquid, and it's also liquid going to gas. It is evaporating and then condensing within the same area, so to speak. So there are different types. You have evaporation and condensation of water, adsorption or desorption of a gas by a solid. That means that the solid is usually your catalyst, and then your gas is attached to it, and from there they can form their products. Dissolution or precipitation of a solid in solution. That means that within a solution, let's say it's water, for example, for the solvent, you have a solute you put in, and it goes back and forth between dissolved and being a solid within that particular solvent, within that solution. Proton transfer in an acid-base reaction, and then transfer of electrons in a redox reaction, which we've talked about in previous units. So in a reaction that is reversible, eventually you end up with something called a state of dynamic equilibrium. That means when we reach equilibrium, that means that the rate of forward reaction is equal to the rate of reverse reaction. We're not saying that the amount of products and reactants are equal. It's just that when the rates are equal back and forth, there's no net change to the amounts of reactants and products. That means it's in equilibrium. When we say dynamic, what we mean is it's always moving in the sense that you're always making reactants and products, but the rate is the same back and forth. One of the things you need to be able to do is be able to graph and recognize the changes that reactants and products make when they reach equilibrium. And something to keep in mind, though, when we do our examples, is that the moles of the reaction kind of impact how much is made for each one. So given the reaction, we have A as a gas plus 2 moles of B gas producing in a reversible reaction. C gas and then plus D gas. The reaction starts with only 1 atmosphere of A and 1 atmosphere of B, and there is no C or D in the flask. Sketch a graph to show the reaction as it proceeds to equilibrium. Upon reaching equilibrium, there is about 8 atmospheres of A. So we're looking here. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10? No, point. Sorry, point 1, point 2, point 3, point 4, point 5, point 6, point 7, point 8, point 9, point 1.00 atmospheres. So we're starting with 1 atmosphere of A and B. So this is going to be right here. Upon equilibrium, A is going to reach it at about 0.80 atmospheres, which is right about here. So this has to be A. This is B. And then this is C and D right here. Because you'll see that both of them are in the same number of moles, 1 and 1 for C and D. You see that A is a little bit higher than B, because in this reaction, for it to occur, you need 2 moles of B versus only 1 mole of A. So A, B, then C and D are at the same point because you have the same moles of each. Okay. Write an equilibrium reaction for the following processes: the freezing and melting of benzene, the solution of the weak acid HCN aqueous, and the proton transfer between the weak base and the weak acid given there. All right, so letter A, so freezing and melting of benzene. I'm going to do different colors. Letter A, so C6H6. So it's freezing, that means it has to be solid, and melting, it's liquid. So it doesn't matter which one you put which, on which side. So it's either going to be solid or liquid because they're freezing and melting. So I'll make this one the reactant side, solid, and then it's an equilibrium reaction, so double-sided arrow, C6H6, liquid. Letter B, dissolution of the weak acid HCN, aqueous. So you have your hydrogen and cyanide ions. So back and forth, in my equilibrium reaction, you're going to form the hydrogen ions and then the cyanide ions. With the hydrogen ions, what they actually do is that they're actually, with water, they actually undergo a reversible reaction too. So with the hydrogen ions plus liquid water, they're actually going to produce, they're going to produce hydronium ions, H3O+. So you may see that at some point. Last one, letter C, the proton transfer between the weak base and the weak acid. So we have HS minus and then H2PO4 minus. So when we're talking about weak acids and weak base, you have to remember that acids donate protons. So we have HS minus plus H2PO4 minus AQ. In my equilibrium reaction, my H2PO4 1 minus will donate a hydrogen to the base. So if this is my base and acid, I have to have the conjugate base and a conjugate acid too. So my conjugate base will be my weak acid that lost a hydrogen, so it'll be HPO4 2 minus, because it lost a hydrogen, plus H2S, aqueous. All right, so that is topic 7.1. Let me know if you have any questions.